Hi everyone, I'm Suman Guha. I'm an assistant professor at the Department of Statistics, Presidency University, Kolkata. And the title of my talk is Gaussian Linear Dynamics, Spatio-Temporal Model and Time Asymptotics. So let's start. So we start with discrete time spatial time series data. They are nothing but time series data knitted together spatially. So we have observations at arbitrary spatial locations at regular intervals of time. So these type of data sets are mostly modeled by linear dynamic spatiotemporal models, which are nothing but linear Gaussian state space model. While the finite sample properties of these LDST models are well studied, the corresponding literature on their asymptotics mostly rely on the associated literature on linear state space model. And hence they are very restrictive in the sense that they assume the covariate process, the covariate information that is stationary with respect to time, which is very restrictive. So our main contribution in this work is to relaxing this assumption of stationarity of the covariate process. And in our work, we have shown that even if we work with covariate process that are not only stationary, but that are changing with time and changing maybe at a polynomial growth rate, we still can prove strong consistency of the classical maximum likelihood estimator as well as the Bayesian map estimator. So let us first consider our model assumption. So we specify a linear dynamic spatiotemporal model, which is basically a Gaussian state space model of the following form. So this is the observed process that is associated with the latent or states process through the observational equation. This P is a known matrix, beta is a unknown scalar quantity, which is a parameter. Then ZT gamma, this ZT is a matrix of covariates, and gamma is associated regression parameters. And these are also again unknown. And then we have associated noise process. The noise process is temporally independent as well as spatially independent. Whereas the second equation, that actually is the evolutionary equation that determines how the state process is evolving with respect to time. And that involves an unknown parameter, matrix valued parameter A theta, and a noise process eta. Now this eta noise process, that is temporally independent, but now it is spatially dependent, unlike the previous noise process epsilon. And regarding the initial starting process, we assume that to be deterministic, not a non-random quantity, something which is deterministic as well as known. Now under this model assumption, first we shall prove, or we shall show, that the maximum likelihood estimator is strongly consistent. But that cannot be proved under completely arbitrary condition, but we have to have some restriction on the growth rate of the K covariate process. So this is our theorem number 1. Suppose Z transpose Z, which is basically a matrix, and we can consider the lambda max of Z transpose Z is the maximum eigenvalue of this matrix. If that is growing at a slower rate than t to the power half, then the maximum likelihood estimate of the A theta, the beta square sigma eta, and sigma square epsilon are strongly consistent. Note that beta and sigma eta, they are not separately estimable, but if we consider beta square sigma eta, that is estimable. As an example of this result, consider the following case where we have only one covariate. So we are assuming K equal to 1. We can easily give an example with multiple covariates, but that is difficult to visualize. So we are working with only one covariate, and that covariate is changing with time in the following way. So although it is not very realistic because the covariate information is actually going to 0, but still it is a time varying covariate. And in that case, one can easily show that lambda max of Z prime Z is like growing at the rate of log t. So this condition is satisfied, and so the MLE of A theta, beta square sigma eta, and sigma square epsilon are jointly strongly consistent. Similarly, if we work with again a single covariate, and the covariate that is changing with time in the form of 1 by t, a spatially varying trend curve, then also one can show that lambda max of Z prime Z is something bounded, and hence the condition of the theorem 1 is satisfied, and A theta, the MLE of A theta, beta square sigma eta, and sigma square epsilon are again strongly consistent. However, the condition that the covariance, in this case, the condition was that the covariate process is actually going to 0. So if we have a restriction like this, that lambda max of z prime z is o to the power small o of t to the power lambda, so small o of t to the power lambda, or since lambda is strictly less than equal to half, so it is growing at a slower rate than square root of t, that enforce that the covariate process have to go to 0, which is a non-realistic assumption. So let us consider a realistic situation where the covariate process is not going to 0, or even if it is going to 0, is not going to 0 very fast rate. So if we somehow put a restriction that the covariate process is not going to 0 very fast, then we can have a strong consistency result for the associated regression parameter. Remember, the previous strong consistency result was only for the a theta beta squared sigma eta and small sigma square epsilon, those parameters. So those parameters, the associated maximum likelihood estimator, are strongly consistent. But we are not talking about any strong consistency result for the maximum likelihood estimator associated to the regression parameters. So now we have such a theorem for the regression parameter. Suppose the minimum eigenvalue of z prime z is growing like t to the power lambda 1, and the maximum maximum eigenvalue is growing at the rate of t to the power lambda 2. Suppose that both lambda 2 and lambda 1, they may be different. So they are strictly greater than half. So, and also lambda 2 cannot be too much different than lambda 1. It have to satisfy a condition that lambda 2 have to be strictly less than 2 lambda 1. Then the gamma hat MLE is also strongly consistent, or the maximum likelihood estimator associated to the regression parameter is also strongly consistent. Now this condition that the minimum eigenvalue is growing like t to the power lambda 1, where lambda 1 is strictly greater than half, actually ensures that the covariate process cannot go to 0 very fast. Also, this restriction that lambda 2 is strictly less than 2 lambda 1, that means when we have multiple covariates, although the covariates may grow in a different way, they may grow at different rate, but they cannot be too much different. Now some illustration of the previous case. Suppose a covariate is growing like 4th root of t, then one can easily show that the MLE of the regression parameter is strongly consistent. Similarly, when it is constant, the covariate process is constant, then again the MLE of regression parameter is strongly consistent. So it's true for the linear growth rate as well as quadratic growth rate. Now all these are results for either for separately for the regression parameter or separately for the other remaining parameters. But we want a condition, we want a theorem which give strong consistency of the maximum likelihood estimator of all these parameters together. So in this regard, we have the following theorem, the theorem number 3. So in addition to the conditions of the theorem 1 and theorem 2, now we have an additional restriction that lambda 2 is not only strictly less than 2 lambda 1, but it is also strictly less than lambda 1 plus 1. Then under this condition, one can easily show that the joint maximum likelihood estimator of the a theta beta squared capital sigma eta, the sigma square epsilon, as well as the regression parameter gamma is jointly strongly consistent. So a demonstration of the previous theorem is, suppose we have two covariates, k is equal to 2. One covariate is growing like t to the power 3 by 4, another covariate is growing like t, then the condition of the above theorem is satisfied, and so the MLE is jointly strongly consistent. However, if one covariate is growing like t and another covariate is growing like t squared, so they're growing differently like previous case, but now their differential growth is too disproportionate, so we cannot apply the above theorem like the previous case. So in this case, we cannot show or strong consistency using the previous theorem. Now these are all strong consistency for the maximum likelihood estimator. Similarly, we can assign some priors on the parameter space, and also similar strong consistency theorem holds for the maximum a posteriori estimator or the associated Bayes estimator. Now here by Bayes estimator we mean map estimator, not the classical posterior expectation type of Bayes estimator. Only a mild condition on the prior is needed, that the prior density have to be bounded. Now these are The previous one are the strong consistency result. Now we can similarly have some rate of strong consistency result that says that not only these difference are going to 0, but if we multiply t to the power 1 by 8, almost like t to the power 1 by 8, actually it should be t to the power 1 by 8 minus some c, for c arbitrarily small, but you can assume it to be multiplying with t to the power almost like t to the power 1 by 8, then the difference multiplied with t to the power 1 by 8 still go to 0 almost surely. So these are some rate of strong consistency result. So like we have three theorems for strong consistency. Similarly, we have three theorems rate of for rate of strong consistency results as well. In a nutshell, our approach is different than the existing approach in the sense that the existing approach mostly rely on techniques from linear state space modeling, and there they assume open parameter space and differentiable likelihood function, but we are not assuming that. And secondly, also the existing approach, they rely on heavily on ergodic theorems, where our approach essentially used tools from uh, concentration inequalities on stochastic process, functionals of stochastic process. But most importantly, the way our result is different than the existing literature is that we don't have any restrictive assumption regarding the growth rate of the covariate process. So that result can be also extended to the non-Gaussian distributions. These were for Gaussian case. So that is an ongoing work. These are some references. And thank you.